Today we deal with thermodynamics. Thermodynamics is the branch of chemistry which deals with the change of heat energy in chemical reactions and physical changes, especially chemical reactions. The terms that we use in thermodynamics introductory sense are systems and surroundings. System means anything under study or investigation. Anything under study or investigation. Surroundings means everything except the system relevant for the study of the system. Anything except the system that interacts with the system. That's the surroundings. Types of changes that are relevant under thermodynamics we'll deal with now. The types of changes are isothermal, isothermal changes. Isothermal means the same temperature, no change in temperature. The temperature remains constant. In other words, you can say delta T equals 0. That's the meaning of isothermal. Isobaric is another term. An isobaric process is one in which the pressure remains constant. That means delta P equals 0. Isobaric. Bar is related to barometer, the instrument that measures pressure. Isobaric means pressure remains constant, or delta P is the isochoric. That means the volume is constant in the process. In other words, we can say delta V equals 0. Another process, type of process is adiabatic process. Adiabatic. In adiabatic process, the quantity of heat remains the same. In other words, delta Q is equals 0. There is no exchange of heat. Adiabatic means no exchange of heat. Another type of process, adiabatic, no exchange of heat. The quantity of heat remains the same, or delta Q remains 0. And now you think about another various types of processes are there dealt with in thermodynamics. We have mentioned a few more I just mentioned. Cyclic process. A cyclic process is one which has series of steps takes place for the process, and ultimately it comes back to the same state. Say step 1, step 2, step 3, step 4, like that. Several steps of processes take place, and finally it comes back to the original state. That means we can say it is a cyclic process. Cyclic process. Cyclic process remains after a series of changes. After a series of changes, the original state is regained. Then you call it a cyclic change. Now you have reversible and irreversible processes. Reversible. A reversible process, as the term itself indicates, is a process that can be reversed to attain the original state, reversible state, a reversible state change. I just cite one example, H2 plus I2, reversibly giving 2HI. It is a reversible process. Another one, a physical change, ice to water and water to water vapor. Water vapor. Or you can think about, say, steam. Steam when condensed, you get back the water. When water is further condensed, you get back the ice. So this is a reversible process. The first one is a reversible chemical process. Second one is a reversible physical process. Irreversible means just the opposite. Irreversible. The process cannot be normally reversed. I cite one example. Say NaCl solution mixed with AgNO3 solution. Sodium chloride solution mixed with silver nitrate solution, you get a precipitate of silver chloride precipitated plus NaNO3. This is an irreversible process. Now these are some of the types of processes that you come across under thermodynamics. Now let us think about the state functions. The state functions. Under thermodynamics, let's familiarize with the idea of state functions. The state functions are state functions. Pressure, volume, temperature. Pressure, volume, temperature. Then internal energy, I will explain each of the terms. Internal energy E, enthalpy H, enthalpy of or heat energy H, free energy G, Gibbs free energy, sometimes we call it, that's why we use the term G to indicate free energy, Gibbs free energy, and entropy, capital S. These are the state functions that we come across under a treatment of thermodynamics. The state functions that are more relevant, important under thermodynamics are internal energy E, enthalpy H, Gibbs free energy G, and entropy S. Let's think about these terms in a little more detailed way. First of all, internal energy. Internal energy E is actually a combination of several contributory terms, factors. One is the energy of translational energy. Translational energy. Think about a sample of a gas, any gas, nitrogen or oxygen or hydrogen, and or carbon dioxide or ammonia. And if you think about the individual molecules, it's evident that, say, think about carbon dioxide for example, the molecules would be moving around rapidly, so transition from one place to one point to another. Translation energy, that involves energy, of course. Translation energy, rotational energy, rotational energy, rotational. The molecules will be rotating about a fulcrum, a central point. There will be rotation. And another is vibration, vibrational energy, vibration, energy of vibration. The molecule, any molecule vibrates about a central point. And another is bonding energy. In any molecule, there are chemical bonds, and if it is hydrogen, HH bond. If it's carbon dioxide, you have C double bond O, double bond O, and that means bonding energy, E bonding, plus E electronic, E electronic. Now, in any molecule or atom, there are electrons, and the electronic state will also contribute to the total energy, that is internal energy of the sample that we are dealing with or we have chosen for study. The sample, the subject for study has internal energy. Internal energy is, as I have indicated, I repeat, E translational plus E rotational plus E vibrational plus E bonding plus E electronic, etc. Now, the other term, the other thermodynamic term that we have mentioned is enthalpy H. H is equal to E plus PV. E plus PV. Internal energy plus pressure into volume, pressure volume. And delta H, according to this, delta H would be, delta H is equal to delta E plus P delta V under constant pressure. If you retain the pressure of the system constant, then the internal energy changes, the volume changes, the enthalpy also changes. Delta H is equal to delta E plus P delta V. And we all know that PV equals nRT, and in that case delta V is equal to P delta V can be written as delta nRT, that is equal to delta E plus delta nRT. Delta nRT. You are aware of the meaning of R, the gas constant, T is temperature Kelvin, and delta N, you should remember the meaning of delta N. Delta N is the number of moles of the products minus the number of moles of the reactants. Number of moles of gaseous products minus delta N is number of moles of the gaseous products minus number of moles of the gaseous reactants. Let me clarify with an example. If you think about, say, a simple reaction, C solid plus O2 G, when you write any thermochemical equation, that is an equation which indicates also the energy change involved in the reaction. You indicate the physical state of the substances involved in the reaction. The physical state, solid, liquid or gas, within brackets. C under normal conditions is a solid, carbon is a solid, therefore you put S, small s, to indicate that it's a solid state. Oxygen under normal condition, of course, is a gas, therefore you indicate G within brackets. That is, for thermochemical equations, the physical state is normally indicated giving CO2G. C plus O2 giving CO2G. In this reaction, of course, the number of moles of the products is 1 and the number of moles of gaseous products is 1, number of moles of gaseous reactants is 1, therefore delta N is 0 for this. Delta N equals 0. Let me take another example, H2 plus I2, H2G plus I2, solid. Iodine is in the solid state normally, and this one giving 2HI. HI is in the gaseous state, therefore you have 2 moles of gaseous product, only 1 mole of gaseous reactants. Obviously, the value of delta N for this reaction would be 2 minus 1. Delta N equals 2 minus 1 equals 1. If you think about N2G plus 3H2G giving 2NS3G, obviously there are 2 moles of the gaseous product and 3N2 plus 3H2 giving 2NS3. Therefore, 2 moles of the gaseous products and 1 plus 3, 4 moles of the gaseous reactants. And therefore, the value of delta N in this case is 1 mole, 3 moles and 2 moles. 2 minus 3 plus 1. So, delta N for this reaction is equal to 2 minus 4, that's 2 minus 4, that is minus 2. 2 minus 1 plus 3, that is minus 2, delta N. You might have noticed one special point. One of the cases, delta N equals 0. If delta N happens to be 0, think for a moment and find out this peculiar situation where delta N is 0. If delta N is equal to 0, the second term on the right hand side in this expression becomes 0. That means delta H equals delta E. That's also to be specially remembered. This is a special case. And in some reactions, if you have to find out whether the values of delta H and delta E are the same, you have only to look for the value of delta N. If delta N for the reaction happens to be 0, that means delta H equals delta E when delta N equals 0. So, delta H equals delta E, the condition is when delta N equals 0. There are instances where it happens like that. C plus O2 giving CO2, we have already seen that example.